Hi, I'm Dongkwan. In this video, I'm presenting our work Unlocking the Potential of Unlabeled Data in Semi-Supervised Domain Generalization. Our paper has been published in CVPR 2025. Let me start with the motivation behind our work. In semi-supervised domain generalization, previous studies have primarily operated based on pseudo-labels. This approach has a significant limitation. It only utilizes confident unlabeled samples for learning, while discarding all unconfident unlabeled samples whose class predictions are uncertain. As you can see in the illustration, existing methods cover only the confident unlabeled samples above a certain threshold, leaving a substantial portion of potentially valuable data unused. This raises an important question. How can we utilize the information from these unconfident samples that have been overlooked? To address this question, we conducted a simple yet insightful observation. We found that unconfident samples are typically confused between a relatively small number of classes, not across all possible classes. More importantly, in most cases, these confusing classes actually include the ground truth class. This insight is crucial because if a sample is confused between, let's say, two classes, it provides valuable negative information, specifically that the remaining C-2 classes are very likely incorrect. We call this the excluded class set E. This observation forms the foundation of our approach. Building on this observation, we utilize information about the excluded class set E obtained from unconfident unlabeled samples as negative pairs in a contrastive learning framework. Our contrastive learning module serves as an auxiliary component that enhances the existing learning process by providing guidance to both confident and unconfident unlabeled samples. Our goal is threefold. First, overcome the limitations of existing pseudo-label-based semi-supervised learning methods, which suffers from poor generalization performance due to repetitive learning on a small amount of data. Second, prevent bias toward a very small amount of labeled data, which typically represents only 1 to 5% of the total dataset. Third, learn meaningful information from the majority of unlabeled data, which comprises up to 99% of our training dataset. Now let me explain our method. We propose UPC-SC, which consists of two key modules. The first is the Unlabeled Proxy-Based Contrastive, or UPC module. In this module, unconfident samples act as additional negative pairs for confident samples. Specifically, for a confident sample with pseudo-label Y, we use the corresponding classifier weight as a positive pair, while negative pairs include classifier weights from different classes, confident sample with different pseudo-labels, and crucially, unconfident samples whose excluded class set contains Y. This allows us to leverage previously discarded data as meaningful negative examples. The second component is the surrogate class, or SC module. Its role is to provide guidance even for unconfident unlabeled samples. We generate virtual prototypes by weighted averaging class candidates based on their confidence scores. The criterion for dividing candidate class set C and excluded class set E is whether the confidence exceeds 1 over the number of classes. In the SC module, unconfident unlabeled samples are paired with surrogate class prototypes as positive pairs. The negative pairs include classifier weights from excluded classes, confident samples from excluded classes, and other unconfident samples with non-overlapping candidate class sets. This enables us to provide meaningful training signals even for the uncertain samples. Here's the overall architecture of our UPC-SC method. It's designed as a plug-and-play approach that can be easily integrated with existing SSL-based baseline methods. The method processes both confident and unconfident unlabeled samples through our UPC and SC modules, while maintaining the original supervised and unsupervised losses. Now let's look at our experimental results. We evaluated our method on 4 widely used SSDG benchmarks: PARS, Office-Home, DigitDigi, and Mini-DomainNet under both 10 labels and 5 labels per class setting. As you can see in the tables, our method consistently improves performance when attached to various baselines. The improvements are even more dramatic in the 5 label setting, with up to 13.1% improvement on DigitDigi. The next slide shows performance improvement comparison between various plug-and-play methods. As shown in the table, our method shows better performances than other plug-and-play methods in most cases. Our evaluation study reveals the contribution of each component. The UPC module and SC module each provide significant performance improvements when applied individually, and when applied together, they show synergistic performance improvements. The graph at the right shows the accuracy of whole unlabeled samples during training. Our method consistently achieves higher accuracy on unlabeled source domain data compared to the baseline, demonstrating that we are effectively utilizing previously discarded samples to improve the learning process. The TSNE visualization clearly shows that our method enhances class-level discriminability in both source and target domains. You can see much cleaner class separation and better clustering even in the presence of domain shift, indicating that our approach successfully learns more generalizable representations. To wrap up, why does our method work so well? Existing pseudolabel-based methods have a fundamental weakness. They tend to perform self-training on small amounts of data, leading to overfitting and poor generalization. Our methodology, which utilizes all available data evenly, is advantageous in achieving high domain generalization performance by preventing overfitting. This is all for today. Thank you for your attention.